Well, on page 2, we have question 15 that asks to use the squeeze theorem. So question 15 asks to use a squeeze theorem and prove that the limit of this function, which is x squared minus 16 times cosine of 1 x minus 4 squared plus y squared, y, x and y, they approaches 4 and 0. It has a limit and calculate the limit. Very well. Note that here you have cosine function. If you remember cosine function, cosine of x is bounded between -1 and 1. So cosine of x, -1 and 1. So you can check to see if this function, cosine of this quantity, is actually limited between -1 and 1. That's up to you. Cosine of 1 over x minus 4 squared plus y squared is actually sandwiched between -1 and 1. Very well. X approaches 4 either from right-hand side or from left-hand side. I'm going to show you how to use x approaches to 4 from right-hand side. X approaches to 4 from right-hand side. It means that your x squared minus 16 is positive. So if I multiply all sides by this quantity, I don't see any change in the direction of my inequality. So I have -1 times x squared minus 16. I'm multiplying this side by x squared minus 16 less than equals to 1 times x squared minus 16. Then I start taking the limit. I'm taking the limit while x approaches 4. And y approaches to 0. Taking the limit while x approaches to 4 and y approaches to 0. Very well. The limit while x approaches to 4 from right or left is equal to 0. The limit while x approaches to 4 either from left or right is going to be 0. So sandwich theorem says since the limit of the left bound, limit of a right bound, both of them are equal to 0, the limit of this function must be 0. Now your job is to check to see if x approaches to 4 from left-hand side, you get the same result or not. It actually gives you the exact same result, that the limit is equal to 0. So by using squeeze theorem, you actually show that the limit is nothing but 0. Well, question 16 said, shows that the function is continuous. Continuous. This is question 16. Here you have your function, which is defined as a pairwise defined function, which is x squared plus y squared for all points x squared, satisfying this inequality less than 1. And if x squared plus y squared is greater than or equals to 1, then the outcome is equal to just 1. You want to show that this function is continuous or not. Is this a continuous function? Well, we have to check all conditions for a function to be continuous. Very well. So let us take a look at your function. Very good. So take a look at the first definition of the function. You have x squared plus y squared. You might say that, hey, I have x squared plus y squared less than 1 for points inside the circle or inside the disk x squared plus y squared less than 1. We have f of x and y equals to x squared plus y squared, and we know that this is just a polynomial and it is continuous. It is a polynomial and it is continuous. For the second part, for points that are greater than or equals to 1, the points that are actually satisfying this inequality, you have a constant function. Constant function is always continuous. For points satisfying x squared plus y squared greater than 1, we have a constant function, which is f of x and y equals to 1, and we know that this is also a continuous function. It is continuous. What about the circle itself? What about the boundary points? Now, for the boundary points, the circle itself, the points that are actually on the circle. Very well. First, I'm going to write this function in polar form, f of r cosine theta, r sine theta is equal to. So note that I have a function that is actually defined as x squared plus y squared. So r squared cosine squared plus r squared sine squared is equal to r squared, while r squared is less than 1. And note that r as a radius, it cannot be negative. So r is sandwiched between 0 and 1. Very well. And here you have r squared, or just r, greater than equals to 1, and the outcome is equal to 1. Very well. So I'm checking r equals to 1, and the limit from left must be equal to the limit from right. Then I can talk about the continuity. So the limit of f r cosine theta, r sine theta, while r approaches 1 from left, and the limit of function f r cosine theta, r sine theta, while r approaches 1 from right. I'm checking both of these. From left, so I'm approaching to 1 from left. I'm using this definition of the function, which is r squared, 1 squared, or 1. R approaches 1 from right-hand side. R is getting closer and closer to 1 from right-hand side, so I know that I have a constant value. And these two are equal to each other. Limit from left is equal to the limit from right. So the limit exists, and it equals to the value of the function while r is equal to 1, which is 1. So we just proved that the function is also continuous on the boundary, which is a circle. So we're done proving continuity of this function. Well, for question 17, we have a piecewise defined function. A piecewise defined function is defined this way. 17, f of x and y is equal to. So if xy is not 0, we have 3 to the x minus 1 times sine of y divided by xy. And if xy is equal to 0, it means that we are trying to include 0 and 0 in the domain. We define the function to be ln of 3. So our goal is to show that this function is continuous at 0 and 0 or the origin. First of all, we have to check 3 conditions. The first condition is that 0 and 0 is actually in the domain of the function. So we defined it here. Second of all, the limit of the function must exist. Limit from left must be equal to the limit from right. So let us check to see if that's true. Limit of the function while x and y approaches 0 and 0. Let's take a look at the limit of the function. Here you have 3 to the x minus 1 sine y divided by xy. Okay, if I plug in 0 and 0, it doesn't give me any information that I actually use. So I can write this, I can separate these limits into limit of 3x minus 1 divided by x times limit of sine y divided by y, x goes to 0 and y goes to 0. So as you all know from elementary calculus, the limit is equal to 1. And here, if you plug in 0, you get 0 divided by 0. By applying L'Hopital rule, you get ln of 3 to the x divided by 1. And this is actually the limit while x goes to 0. When x goes to 0, you have ln of 3 times 1 divided by 1 times 1, which is equal to just ln of 3. Very well. And the condition, final condition, we need to show that the limit is actually equal to the value of the function at 0 and 0, which you actually can see it here. So on the exam, you need to list all of the 3 conditions and prove them one by one.